Okay, so here's the lecture on the recording, the lecture on steel castings. Now, I'm going to admit that I haven't done this lecture in 6 years, and I made it 7 years ago, actually closer to 8. So some of it's coming from memory, and I'll also admit that I was selling castings at the time. As much as I was also doing technical work and engineering for them, I was also one of the people going out there in the world, and at the time there was only like 4 or 5 of us working for the company, convincing architects and engineers in North America that steel castings were a useful thing. It was something that was done a lot in Europe, but no one really here had the engineering experience or the production experience to make castings for architectural and structural kind of components. So I was touring North America and different conferences, talking about castings. I got to go into a lot of really amazing architectural firms throughout North America. I was in Diller Scofidio, been in great engineering offices, Thornton Tomasetti, Walter P. Moore. Oh my gosh, there's so many other architects. Guy Nordinson, Blackwell. A lot of the local architect firms who were already kind of my pals, so it was kind of nice to get in there and talk it up, going across Canada as well. Got to go to AIA quite a few times. So some really kind of, well, the story that Dave told when there was the tornado in Denver, that was the year AIA was in Denver, and there was a tornado at 2:30 on whatever day, and I was flying in at 2:30 the next day. So I missed the tornado by 24 hours exactly. And I had almost been on that flight the day before. So, I really got to be exposed to some amazing designers, both engineering and architectural, throughout my time with Cast Connects. But this is the slideshow I did for them as a salesperson, more or less. So it's going to read a bit different than most. I'm not trying to sell you castings right now. I'm trying to show you that it is a reasonable option for certain design ideas. So let's go through some of those slides. So these were the main ones that Cast Connects were working with. I'm going to change my mouse here to make it a little bit easier to see. Mouse settings. Just hold on with me, bear with me for a sec. I'm going to adjust this cursor so that you can see it. There, so that's a little bit better. The custom nodes are kind of the really fun one that you guys are going to care about the most right now, I think. They have a few other architectural ones, and then for the people that are really kind of engineering driven or really technically driven, I'll touch on the high strength connectors and the Scorpion as well. They have even more products now. Obviously they had been operating for several years, kind of by the time I was brought in, and when I left, they were just on the verge of doing like some truly extraordinary stuff. And they have grown so much, it's incredible, and I'm so proud of those guys. So this is just a little bit about Cast Connects. I'm going to skip over that because I'm not trying to sell you the company, I'm trying to sell you a thought process, or tell you about a thought process. One thing that is cool though, these two guys met at, well actually they met at Yallus, but they were both going to U of T. Carlos has his master's in engineering, structural engineering, focusing on castings, and Michael has his PhD in structural engineering, focusing on castings. So ridiculously smart dudes, really fun guys, really sweet gentlemen as well, and I'm really lucky to call them my friends still. So what is a casting? Casting is taking a liquid and pouring it into a mold containing a hollow cavity of the desired shape and allowed to solidify. I don't say melted and cooled because that's not always the case. The ones we're talking about, it pretty much is the case, but the definition of a casting is pouring something liquid into a mold and allowing it to set. If you've made Jell-O, you've made a casting. Sometimes you have to break the container that it's in to get it out, or you lose the mold, but sometimes you get to reuse it. It depends on the type of casting it is. So these are all things that can be cast. These clay bricks cast. These toy soldiers, it actually used to be that you made your own. You melted down like an aluminum tin composite and pour them into molds, and then you would paint them. That was how, back in your day, right, Dave?
Sorry?
Nothing, never mind. Never mind.
In that case, yes.
No, I just called you really old, essentially. Your cast iron frying pan is a cast piece of iron. Bundt cake, Jell-O, all castings. Castings have been around for a ridiculously long time. Even in metal, they've been around for a long time. So cast copper, we have images or elements of cast copper from over 5,000 years ago. So it's a process that we've been working with as humanity for a very long time. But the type of casting that we're used to talking about now is pretty recent. So the present day castings have only been around for 100 years or so. It was so prolific that it actually even made it into the art of ancient societies. So here's a Greek vase showing an iron manufacturing furnace. So this was them getting ready to cast, or a method that they would use to make castings. Just a few more, just showing casting being part of the art world. So cast iron, it was castable, really easy to cast with, but really hard to weld, and most grades are brittle. So cast iron, brittle, and hard to weld. That's why most ironworks that you see that are older aren't welded together but have rivets or elements driven through them, holding them together. So this is, you've probably seen this bridge in a gazillion pictures. It's kind of a really famous bridge. It's an iron bridge built in 1779. Honestly, or ironically, not ironically, I don't know. It's the bridge to get to a foundry. It was to be able to take more iron away from the foundry. So it became a famous piece of architecture. Cast steel is ductile. Ooh, you gonna get me one of those?
You want a peanut butter?
I would love some peanut butter on bread, sourdough bread. Thank you. My sourdough starter is back and running. I had killed them off for a little bit there in the summer because it was too much to maintain, but we've got sourdough bread back in the house, and it's delish. So cast steel, however, is ductile. So not iron, but steel is ductile, and it has... Had you already made this for me, or was this for you?
For you.
Aww. I am going to apologize. I'm going to eat peanut butter, so it's going to be a bit sticky in my mouth. Sourdough, so it's a little bit crusty. It's really easy to cast with. I mean, once you have the system set up, you can't go cast steel easily in your backyard. But the big thing, it's weldable. And it being weldable is really important to incorporate it with the rest of the structure. So, Pompidou Center keeps coming up in our different lectures because so many things about it from a structural or an items in structure standpoint, really, really fascinating. So these Gerberettes that I showed you in the complex geometry lecture, are cast elements, and I'll show you some images of that further in the lecture. So, this must have been the lecture series for architects, which is perfect. People have it in their head that castings are brittle. And that comes back to the fact that most castings were actually iron, which I already showed you is brittle. But cast steel, very, very different. You guys remember your stress strain curves from structure 2. If we go up and we get out of our elastic zone and we have failure, that's brittle. If we have the ability to have large deformations without an increase in force, that is ductility. It's permanent deformation, but that energy is absorbed in there. And then we have our ultimate failure. So that is a ductile stress strain curve, and that is a brittle stress strain curve. We like ductile in buildings. There's a few reasons. We can see a problem long before there is major damage. And it's really good at absorbing energy, which is wonderful when we're talking about seismic loads. So, brittle, you drop this thing and it fractures. Ductile, we can get large movements without it failing. So this is actually one of the structural, one of the casting elements, the scorpion. It looks different now. This was some of their preliminary testing. But this is the same object seconds apart. That is an inch thick piece of steel. And there's 1, 2, 3, 4, 5 of them. You can, on each side, you can imagine the amount of deformation that is happening to get from this to this without failure. So that is ductile behavior. So, sorry. Sing for me, Dave. Dance. Do something. Entertain the crowd.
No, I'm just obsessing by the peanut butter on your face.
He'll eat peanut butter on anything. When I was pregnant, we had something, and there was a leftover half a loaf of, or half a head of lettuce. He took the lettuce and smeared peanut butter on it and ate it like an apple. I was the one with pregnancy cravings. He was the one eating the weird shit. So, here are some images of castings from other people. A lot of them you're going to see are in Europe, which is where cast structural elements was and is still pretty popular. They have the foundries, they have the engineering, they have the means to do it. It's kind of a lost art here in North America. Places you see castings actually quite often, something like a wind turbine, and these complicated nodes. Here is an architectural feature. The casting joint isn't actually right here. If you look closely, you can see right here and right here is where the slight imperfections are, where they've welded the tube to the casting. And rather than have that be seen as a flaw, nearby they put an architectural feature to draw the eye to it so that this almost disappears from view compared to this controlled cast-in feature. This is the Munich pavilion, right? I forget all the names of all the different projects now. And I get this one confused with another one.
With the one in Montreal? Yeah, I think that's the Olympic Park.
That's right. So, we've talked about this for other projects. In complex geometry, we've talked about it in tensile structures, but it comes into play in castings. It's kind of clear here that innovators are innovators, really. Like, if you're willing to do cool shit, you're willing to do cool shit on everything. But those nodes right there are cast. Here is, so just to give you a sense of the scale, that's two people carrying not the casting, because that casting would be crazy heavy. This is the positive mold of the casting, and we're going to talk about the casting process in a little bit, and that'll be a bit more apparent where that comes from and why that would be. But there's a close-up of that casting. It's just absolutely gorgeous. I love that kind of tapered or curved element to it there. The Gerberettes on Pompidou, again, a sense of the scale. You can see here's the casting, and it looks kind of rough and messy. You can see its complex geometry where it's accepting multiple different elements to join in. This is actually a really unique project in London. Not just the nodes are cast in this, but the actual tubes are cast into it. It's part of the lateral system. And the reason these were all cast is they wanted to use it. This was near a, oh my god, that was so yummy. Thank you. This was near the subway station. And in the event of a catastrophe of some sort, they wanted this to be a refuge, and they wanted to be able to pipe kind of think of a sprinkler system, but like an industrial level sprinkler system through the tubes here. So all of these are stainless steel, and they're, I can never pronounce this right, centrifugically cast. Did I say it right?
No.
Centrifuge. It's a centrifuge.
Yeah.
Centrifuge.
Centrifugally?
You're messing with me now. You're screwing with me. Or do you not know either?
Centrifugally.
So, they're cast using a centrifuge, which is basically you put the liquid steel in it, or the molten steel, and you spin it really, really fast, and it puts it all out to the outside edges until it's cooled. Not the norm, and you'll see there's even a question in the assignment too, because it is not the norm for structural elements, but it can be done. It is a method, but it certainly isn't the norm. But we can use it for, I forget how I worded the question now, but can it be used structurally? Yes. It's not the norm, but it can be used. In the end, they spent a ridiculous amount of money for this, and it ended up not being used in that method because I think the ultimate route of the subway got changed, and it never went underneath this building in the end. So here's just another image of it. Here is, again, a really gorgeous casting where the connection isn't right here. This is detailed into it to draw the eye away from where the connection would be taking place. Every time you're typing, something is shaking and it's driving me nuts. There's like the filing system over there or something is. It's you. No, you don't have to. You don't have to unplug your computer. Just move that. Move the metal thing over just a tiny bit. Do you see the big metal filing system?
Yeah.
Yeah. That's probably what it was. That's probably good. Dave, it was like just barely touching something. Let's see. Type. Problem solved. I'm sorry, guys. I'm sorry to break you into our ridiculous, ridiculous life. Okay. So here's another casting. Again, you can see the weld line right here. This is to draw your eye away from it. What I really like is this is casting, they're bringing it down to a pin. This is not actually an articulated joint. It can't move around. We know that what it's trying to do is say, yes, it's allowed to move there. They didn't actually make that casting able to move around, but they've made it so small it is essentially like our true pinned connection. The reason we can have these tapers is that, if you guys remember in Structures 2, compression elements governed by buckling. But you see where the buckling happens. It happens here in the middle of the element. It doesn't happen here at the connection points. So up here, it's just about strength. And you remember on long elements, if we were looking at the capacity is quite small here in the middle, but if it had been governed just by strength, you need much less material. And so we can be governed by strength at the end points where it's just about cross-sectional area of the steel. And we don't care about how far away from the centroid that material is. So we can come down to where we're governed just by the cross-sectional area of steel at the ends of our columns or anything that's in compression. And you're going to see that Cast Connects kind of built on that and created an actual kind of off-the-shelf product that solves that for a lot of people. You can see this same idea in play here. This was a Fastinet project where they used castings in wood products. I believe now, when I left Cast Connects, they were in the process of developing a standard line of wood connectors for things just like this, and I think they have that on the market now. So, like I said, these were their at the time their main elements. They've added another one that I know of for sure, which is the ARC, which is basically a taper to their pin connector. So custom elements, they're highly engineering-based ones, and they're universal pin connector. So the Scorpion is the engineering one, where these fingers will actually yield absorbing energy in a seismic system. So the Scorpion yielding connectors are used in the building brace system for seismic lateral load resistance. It's ductile and part of the capacity design system. That's really important in high seismic zones where we want to make sure something doesn't have more strength than it needs, which sounds kind of crazy. But if you allow things to yield just perfectly so that the energy goes into the yielding, we can actually reduce the loads that the building sees. And so we usually control that by having a yielding element or a capacity designed element at a specific spot in the system. And there's a lot of different ones on the market. They've been being developed probably mostly over the past 10 to 15 years. It's a relatively new design idea, and Cast Connects has kind of been out there at the forefront with it. They have a few colleagues that were also developing different cast elements, but their products were less about castings overall and just about the performance of the seismic element. What's great about this one is these elements here can be brought in pieces, and they can be assembled on site. Really important in kind of remediation zones. So northern Quebec, which has a lot of masonry buildings that they're going in and retrofitting for capacity design, because if we've learned anything from major earthquakes in, for example, like in Haiti, that low-rise masonry buildings perform probably the worst, or not the worst, but have the biggest loss of life kind of problems with the failure modes of those buildings. So going in and retrofitting those kind of susceptible buildings with frames that then have capacity design elements in them is really important. So they're great for, remember those post-disaster buildings that I talked about? And then, so what would you guys care about as the architect? Well, it can help reduce, so if this is owner, E is engineer, C is contractor, and A is architect. Where it really comes into play for you guys is it reduces steel and foundation tonnage on elements that are governed by seismic. Not that big of a deal here in Toronto, because we have a pretty low seismic zone. Ottawa, northern Quebec, BC, it can have a big impact on the steel, the rest of the steel that we need. Because if we can use these and lower the actual forces that the building sees, we can actually reduce the tonnage for the rest of the building as well. A really nice thing is that they're simple and standardized. You do your analysis, you figure out what your loads are, and then you can go select it and pick it from a chart, which means the base building engineer isn't spending all of their fee designing capacity elements for their building. High strength connectors are another seismic product. They're better in maybe the less, kind of the less over the top seismic zones. So in around Montreal, Niagara region, it's a higher seismic zone. New Brunswick, these are a really good element to use. And they're slightly more visually pleasing. In fact, when I was working there was lots of architects that just specified these, not for their seismic capacity, but simply because they had better control over the detailing of it. So this is a picture I took on my crappy iPhone in 2012. Where they just painted the seismic connector and ended up leaving it exposed. So it looks, if you guys remember images that I showed you guys of braced frames where you can end up with some really ugly connections, this ends up being quite kind of elegant. So connectors for concentrically braced frames, low to mid-rise buildings. You aren't as interested in the RDR not factors. That's a very engineering-based term. They can be exposed, which is really nice. AESS, so architecturally exposed structural steel standards, if they're part of an exposed brace frame. And the big thing that would be for you guys is it takes the unknown out of the gusset plate connections on drawings. So this is what we tend to draw on our drawings. So these were kind of some sketches I did for the guys way back when. This is what we tend to draw on drawings. This is what we tend to get. You can see we've got a knife plate, a gusset plate. This is welded on, and we've got our bolts here. And this is usually detailed by the fabricator, who have a real incentive not to use a prefabricated element because they get a lot of their fee and their markup on these sort of elements, which isn't wrong. That's what the way the industry was set up. And so you can get some pushback on specifying something like this. But what you can end up with if you do take control of it or get your engineer to take control of it is something that looks more like this. So I actually did a design for all of these three methods and drew these things to scale for, I can't remember what project it was. So you can get these kind of tapered gusset plates, and your connector is really controlled with designed bolts that you just pull right off a chart, which is really nice. Because this is what you can end up with if you leave control to the fabricator. But seismic-wise, what we end up with is a plastic hinge here. I realize that there's some more videos that I didn't include in this that I think I've shown you guys before that are just really cool. I'll add them into the module that you can go back and watch. But it's one where it shows this plate yielding right here, and it shows the column yielding as well under seismic loads and how it can absorb the energy. So this is that same project that I showed you, the photo that I took. This is another location in the project where they then just built this right into their partition. So this one here actually gets hidden. I think the picture I took was down at the base of this one. Here's another one in a slightly more industrial setting. You can see that it's been welded on here and ground smooth because it is going to be an exposed condition. Engineers who aren't used to doing seismic design think it is really, really hard, and it is really, really hard. It's almost a specialty field. Most offices will have their seismic expert or a few seismic experts. In places like New Zealand and BC and California, more of the office would be seismic experts, but usually still you have a team that reviews it, and then in those places it is standard that you have peer review, where all of the firms work together and talk to each other, and they review each other's work as a standard. It is just a given that you do peer review. It's not something we see as often here in our local market. So Cask-Connects, one of the cool things is that they, because of doing all this, they're just seismic experts. Even if you ever have a question about something seismically, they're really kind of great guys. And actually, Dave, you had a project recently. It wasn't seismic, but you were speccing something on the project that was a Cask-Connects product, and they came back and they said, listen, we just want to let you know there might be a cheaper option that's not our product. Here you go. So, you know, they really do want what's best for the project. I know I sound like a salesperson, but it's true. Here's one of their first projects that they got used. Here's where they were actually galvanized. All steel batches galvanized slightly differently. So you can see that because these are two slightly different steel compositions, you can see that they galvanized slightly differently. But that's pretty close to the seam line. So when you stand back, it just almost looks like it's part of the shadow cast, which is kind of an interesting way to do it. So this is the pin connector. So this is a true pin where we can actually get rotation at this joint, which is what we assume when we design things. If you have a large element, remember I showed you guys probably in Structures 1 or Structures 2 an image of one of the bridges over the Don Valley, where they actually had to make a true pin connector, because had they just bolted that to the concrete, it would have made it a moment connection. And once it's a moment connection, we have to design for the forces and everything gets bigger. So sometimes we have to go out of our way to really ensure in our detailing that it is a pin connection. And this is where the pin connectors really kind of come into play and can make that happen. Often used in architecturally exposed structural steel. The CISC handbook, or the CISC kind of AESS, so that's the Canadian Institute of Steel Construction, has an architecturally exposed structural steel design booklet, and in it, the biggest thing that you need is this chart, where it defines what you get with different specifications of architecturally exposed structural steel. If you do nothing, they'll just do what they want, which if it's hidden away, who cares? It's structural, it's not visual, it's not doing anything. You can have basic elements, and that's where they'll grind smooth welds, they'll get rid of weld spatter. As you go up in level, more and more elements will come into play, or the work that the fabricator puts into it on a, not a structural basis, purely on a visual basis increases. And what I like here is the cost premium associated with those things. Where can you use the pin connectors? Struts, columns, braces. So all kinds of different kind of spots where you can make use of those. This is the Whitney Museum. You can see here that they made use of the pin connectors. This is actually part of their seismic system too, but the forces, it didn't need capacity design. and the forces were low, so it was a standard style connection, and they were able to use their pin connectors. If you don't specify their product, a fabricator can make their own. There are alternatives to their universal pin connector, and this is the sort of thing you will end up with. You can see that you've got the plate sticking out, and this is tapered down. It's a little bit bigger and a little bit clunkier. This is actually on a project that Dave did, where he tried to specify he tried to specify the pin connectors. The fabricator had a bit more control in this project and pushed back and said, I'll make something better and cheaper. I don't know if it was cheaper or not, and I don't know if it was better or not, but it met the design intent. It's up to you which one you think looks better. I think I'm not gonna weigh in on that. Here are some uses of the pin connectors as struts. You can see here that this tapers down. In this project, they started to really see that they were getting requests for tapers, and I spent a lot of time designing on their behalf for the base building engineer tapers. So actually taking the base building engineer's contract documents and designing a taper to go from the column to the pin connector. And we were like, maybe we should just offer a line of tapers as well, kind of off-the-shelf tapers that let you go from standard column sizes down to the standard pin connectors. And they have actually done that now. So you can see that not just having smaller, so one of the nice things is that now you're also using a smaller pin connector. We did some kind of cost estimates and even adding in welding and the fabricator carrying the cost of these. By the fact that you're going down to this smaller pin connector, you're actually saving a lot of money because you're reducing a lot of steel here. So this is where we were introducing the art or the architectural tapers. So you can see here's the universal pin connector, and here's the architectural taper. That gets from a 406 HSS down to a 273 pin connector. So these are the things that if you don't specify it, that you can end up with on your project. You can see these are starting to get really big. This actually turns it into a moment connection, which means now this whole thing has to be re-engineered to take moment into all of these things. This is getting really crazy. Really complex methods. Really complex kind of connect methods. This one is actually a seismic one. Here they're trying to do a capacity design. So they're controlling what the force is at those joints there. You can imagine something custom cast here might have made this a little bit easier. There's a lot of site welding happening for this. And if you spec nothing, you can end up with these crazy big things. Here is one of the pin connectors being made in the shop. You can see here that it's 538 pounds. So they're big, they're heavy. This is before the holes are put in it, and it would get ground down smoother and polished up a bit. This is just salesman-y stuff. Okay, so this is the common questions I always got. But it's so expensive. How do I have tolerance? The design is complicated. Fabrication. It's a proprietary product. We need three manufacturers to be able to list it on government drawings, and it adds coordination. So I've done a few price ratios. Up front, it seems more expensive. In the end, and I'll show you one where it ends up not being more expensive. Not to the owner, because the fabricator's bearing the cost no matter what, but the fabricator took a loss because they tried to make the connections on their own. The problem with that is now you have a fabricator who's at a loss and who might have given you leeway on small changes or small items further on in the project, needs to recoup their losses somewhere, and so they're going to fight you over every other issue that might be on the project. Not because they're being jerks, but because they have to. Designing and detailing, Cast Connects was happy to do. I did a lot of that. Design manuals that you can just look up what the forces are. Easy to fabricate because it just gets shipped and they weld it on. You can say cast node or approved equivalent on the drawings. It does leave room that the fabricator will provide something, but if you add the approved, it means that it has to be architecturally, the architect has a say in what it looks like, and can they say it, and it might end up then coming back to the cast node in the end anyway. So if you put no information on the drawing, you can end up with that. The fabricator design looks good. It's probably a flat plate on the end with two side plates here, or ear plates. The Cast Connects one kind of comes down and smooths it out in all three visual directions. So this is the same detail. You can see the gusset plate kind of smoothing out a little bit. Cost differences. If this is considered our basic price, I'm not assigning this a price, but let's call this price 1. Fabricator design for something fancy, let's just call it a fancy factor, you could end up to 3 times to 6 times the price premium. Cast Connects consistently, when I was looking at these pricing elements where people would actually give me back price info, and I actually reached out to a few fabricators to price things, was coming back at 3 to 5 times. So about the same range, but with a lower possible upsell on it for going with a cast element. Here is an example that I looked at in detail where a fabricator produced their own. So this had 1,600 millimeters of AES welding. They had to weld on each of these plates on each side, and then they had to weld the plate all around the HSS. So this would be your basic kind of pin connection that the fabricator would produce. If you told them you wanted an enhanced pin connection, so getting some of that taper down, this is the one where the fabricator on Dave's project produced their own version of it. They now had the taper that they had to weld, and they had these all of these side weldings. When I counted up the linear weld, it was 2,600 millimeters of AESS welding, so that means grinding it smooth and painting it. The UPS connector, 930 millimeters of AES welding. So a lot of times that's a big cost for contractors, especially when it's on site. None of this would need to be done on site, but if it was on site, it would be even more of a premium. But you can see the big reduction in welding here. The ARC and the UPC, the welding goes up, but you get a much smaller connection here. Tolerance. There is tolerance built in here. So if that's the soffit, there is tolerance in that this can be slid into place. So a lot of the fabricator design ones, it's a little bit harder to build in that tolerance, but the guys thought about building in tolerance into their design. And there are design tables that you can just go, engineers can go look up loads. The really nice thing is it's a simple weld. You usually just put it on a turntable, more or less, and you hold it in place and spin it and weld it. So there's no underneath, like looking up welding, which is really difficult, a really difficult thing to do. If it's not seismic, and if it's not, even if it is outside, depending on the condition, rather than have them grind it smooth, as long as they can get the right amount of weld, and this is where Cast Connects can give feedback, they can weld this up to meet the structural capacity listed on the drawings. And rather than over weld it and grind it smooth, they can leave that bumpy and then put Bondo, which is, you can buy it at Home Depot. Put it in there, and then you can sand it down, and then you put your protective paint coating over it. So it really reduces the cost here for welding. How do you deal, this is one that architects and engineers often ask, is there's different wall thicknesses. How do they deal with that? Well, just where it places along the end of the UPC allows you to use different wall thicknesses. So this is a project where the fabricator said, I have these images because it was a Blackwell project, and I know Blackwell had spec'd Cast Connects on the drawings, or equivalent. The fabricator came back and said, no way, we're going to make our own. We can do it cheaper. We're gonna own this. So the fabricator, when they actually got into it, I showed you those weld lengths. This was the approved equivalent, so you can see this plate much more. You can see all of the grinding they had to do to get it to meet AESS standards. Oh my God, I used to have the numbers for this. This was Ian's project, Dave. What was there, 50 of those on it? And I think there was something like 20 hours of grinding on each connector that they had to do. Darn it, I used to have the numbers. It would be their cheapest guy in the shop, but they're probably $40 an hour, right?
Yeah.
So 40 times 20 times 50. Oh my God, that's a ridiculous amount of hours. That's saying 40,000 hours? Does that seem crazy?
Yeah.
20 times $40,000. $40,000. Yeah.
I think that's right.
Yeah. I think I remember that they ended up, it cost them $20,000, and they came back and said next time we're using Cast Connects.
It's such a lesson that a fabricator would sooner spend $100 in their own shop than buy a $75 product.
Yeah, it's true. Sometimes it's because of risk. They don't know. It's an unknown. Sometimes it's because they want to keep their guys employed, or they want to know, it's worth it for them to lose $25 an hour on, or lose that $25 of premium to have steady work. It's hard to know the motivation, and it's different depending on the shop. But once you make something kind of easy and understood, what I found when I was working with Cast Connects, there was a few fabricators in the States that once they used it on a project, they would actually propose it to the architects and engineers as a solution. So I remember there was one kind of repeat fabricator that came back to me again and again and again. I think I had, when I left, 6 projects on the go with them, where they weren't even spec'd in the project. They just found it cheaper and easier to use them. So government projects with sole sourcing. So how do you avoid sole sourcing? You can say buy Cast Connects or approved equivalent. This one was the big hit, cast node designed by supplier. And then they'll ask you for a list of suppliers, and there are other people that can make them, but they might not meet the aesthetic requirements that you need approved. So you've met the mandate of the contract, but it would probably end up going back to Cast Connects. A foundry could bid on it on their own, but it would be more expensive. So you've met that criteria. Or you can say true pin by a fabricator or a casting company. So that would give you that alternative where the fabricator makes their own. So here are other ones that Cast Connects have seen done by base building engineers engineering them and having them put on the drawings. So they weren't specialists in castings, but they became semi-experts, I guess, and had specific products kind of created for a one-off for a project. So that's Cast Connects. So here was a crazy one where I was reached out to by a landscape architect in New York, and they were doing a park, and they had to cut down a bunch of trees to allow them to build the play structures, but they wanted to preserve the trees. So what they were proposing was building something for the ends of the trees that allowed them to reuse them. So completely, they had no engineer at all. So while I was with Cast Connects, I actually engineered a full system for them and foundations, and kind of gave them information on what they could do to make this a buildable solution. The thing is they needed to have tolerance because not every end of the tree was going to be the same. And they needed tolerance for angles because they were going to be at all different angles relative to each other. And they needed to be able to install these on site. So this one was kind of a pie in the sky, but the landscape architect seemed pretty convinced that this was the way they were going to go, and it was on hold when I left. So here's just a close-up detail of the information I gave them on how they could do this. Yeah, I actually designed the sonotubes. And here's, you can see how I gave them tolerance in installation for the different systems. And that's what it would end up looking like with a relatively hidden connector on the end. Okay, the big one, the cool one that you guys want to talk about is custom nodes. So how do you know if custom nodes, hey, do you have 20 minutes?
Yeah.
Could you go, the kids they're doing, it's Diwali tomorrow, and one of the other moms in the class is doing an online cooking thing, and what I don't have is sweetened condensed milk. I have all the other ingredients for the cooking, and I need to be able to do that in an hour. So if I go get it, I can't finish recording.
Yeah.
Would you be willing to go get the sweetened condensed milk?
I have exactly enough time to do just that.
Thank you so much. Just go to Food Basic. Don't forget your mask.
Yeah. How much?
A can of sweetened condensed milk. It's in the baking. It'll be in the baking section.
Okay.
If you're standing right there and you see dried coconut, it's in a package like chocolate chips. Pick it up because I have one bag, and 2 bags would be better because you roll them in it. Sorry. Okay. Custom castings. Are they right for your project? If you have something architecturally exposed and it's steel or a timber connection, castings are a good choice. If it's a complex connection, castings are a good choice. If it's a feature, castings are a good choice. If it's a fatigue critical connection, so what does that mean? If you're worried about light level seismic loads or a repetitive loading condition like wind or seismic again, someplace where you get loads going back and forth and repeating. Gravity load is on there and it kind of stays there, but it's that loading unloading that can kind of wear something down a little bit. So those are all conditions where custom castings are a good choice. I'm not going to lie, this is probably where they make their most money, but hells yeah, they deserve to make the most money there. It's the, like I said with the complex geometry, time and risk. They're taking all the risk, but they're taking all the risk out of other people's scope where it's a higher level risk. So they deserve to get paid because they are bearing the risk, but they're lowering the amount of risk for everyone, and they actually end up lowering the cost overall. I wish I had there's so many cool projects. There's one, maybe it comes up. I'll show you if it comes up. And so the more of those things you have, the more cost effective the castings are for your project. So here's an example where this one was, it had load on it, but it was mostly just gravity load. So this was more heavily on the architectural features side. You can see that it was ground. This one, they left room, and they actually put the Bondo in and smoothed it out down and then painted it. And if you look closely, you can see the joint line right there. So it's really hard to see those joint lines, and right there. So the one I'm going to talk about now is the Queen Richmond Centre, because it's in Toronto. I know all of you aren't in Toronto right now, and you normally would be, but it's in downtown Toronto. The one I wanted to just briefly mention was the Transbay Transit Centre in San Francisco that they worked on. The project came back without them involved, and I can't remember what the price was. They came up with a concept unpaid, and they were able to take $5 million out of the project. So the design team decided to hire them on a design assist basis, and I believe for $10 million worth of project, they were able to take $20 million out. And then there was a third phase in there. I might have my numbers mixed up, but those I think in the end, we ended up saving the project like $20 million. Now, it was a $1 billion project, but $20 million is a lot of money to save on any project. And so they went through various stages of involvement, kind of convincing the team at each stage to bring them on. So this one is in Toronto. It's actually office Dave works in now, because the building we were in forever is torn down now. That was on Duncan Street. Our second son is named Duncan, so you can see that it meant a lot to us. So they're now in the Queen Richmond Centre. At the time, they were & Co, the architect. Now they're Sweeney & Co. The engineer was Stevenson, and the fabricator was Walters. Walters Fabricators, fantastic, absolutely stellar, top-notch fabricators. They're who I worked with for Goldring Center for High Performance Sports as well. So the program for this project is an 11-story reinforced concrete building hovering over a 4-story existing building. So you've seen me talk about this a little bit in the past. They were told minimal impact on the existing facade of that building and the architecturally exposed structure. It had an LED or a LEED gold standard, and they ended up using 3 cast structural steel nodes in the design. So here is the project. You can see it here. So the design discussion. So this would be kind of your preliminary ideas. So these are some overlays I did kind of going back through. So most of this was done before I worked with Castanex. So I went back and dug through kind of some of their communications and looked at the iteration. So your normal standard approach, you would have your 4-story heritage building here. This is your elevator core going up through your building. You would plop some columns down here, and you would punch through the existing building here. This and this would be your lateral system, so you can stop things moving this way and you can stop things moving this way. So that would be your standard. That solved gravity load, and it was easy to erect. It did not solve the visual barrier because there was all of these columns, a field of columns that you could see everywhere trying to look at this facade. And there was lateral difficulties. They were actually told they weren't allowed to connect to this facade because, as you can imagine, this is a existing brick facade that has almost no capacity. Adding in the lateral system of an 11-story building onto the top of it wasn't going to work. So that left just this core as the lateral system. That left torsion problems. So it was certainly something they looked at. So one of the things they introduced was the possibility of delta frames. I realized I had more slides in a different lecture that I gave the PEO that was kind of really interesting, and I wish I'd forgotten about that lecture. So what they suggested was delta frames. And so I don't know if it was the base building engineer or the architect that came up with this idea. But it was going to be difficult to fabricate these nodes. They did bring on Walters very early and discussed it, and they did come up with a possible solution. In there was going to be essentially a steel plate that got welded on site and ground down. It solved the gravity loads, it gave them the visual system they wanted, and it solved the lateral system because now each of those became essentially two-way brace frames, or the delta frame system that they developed. It wasn't easy to erect, and there was eccentricity in the nodes. So the nodes, all four of those things, top and bottom, so 8 things coming together, didn't have centroids or lines of axes that came to a singular point. They were offset from each other, which meant we have forces offset from each other, and you have forces offset from each other, you have a moment. What they needed was 2-inch thick concrete filled HSSs. So that's 1 meter diameter HSSs that are 2-inch thick walls filled with concrete. They have the added problem that they need to pump concrete all the way up through the system. So were they able to make the original design? Could you do that? Yes, totally. So this yellow outline is what you would want, and you would want your work point to be right here. So the centroid of that and that would all come down into that singular point. But they couldn't do that. They needed to be able to weld things together and have concrete pump through, so they had to pull the elements out like this. And this became the column edges, and this would be the plate that they were going to put in and weld in. The problem then is, how do you fill it with concrete? Because they pump it from the bottom and fill it all the way up. They were going to have to, and concrete cures, so they couldn't fill just the bottom and just the top, because concrete, as it cures, shrinks, and they were going to end up with gaps here. So CastConnex came in and talked to the team about options. They were brought in for coordination, design, and finite element analysis. They did the foundry coordination, the tooling, the sand mode, the casting, the enhancement work, the machining and surfacing, the testing, the delivery, and the erection. So these are all things that a base building engineer would have zero expertise in. You might have someone that has a bit of knowledge about these things, but they wouldn't have kind of the precise knowledge on it. They coordinated with everyone on the team, so the architect, the engineer. They were in communication with the owner, worked heavily with the contractor, the fabricator themselves, the erector, and the foundry. So these were some of the very preliminary elements that they worked with. When I would give lectures, I would usually go to an architect's firm and bring a couple 2 floors of beer and plasticine or Play-Doh, and let the architects play with things that they've wanted to build, ideas they've had, and obviously give them beer and wine because everybody likes you more when you do that. I don't know. And this was one of the ideas they came up with. They actually had, it wasn't what the architect was originally showing. They were showing it kind of coming in more in a tighter element here. CastConnects proposed making it look like all 4 elements bent and leaned against each other. The architect really liked that idea, so CastConnects had a model 3D printed. This was back when 3D printers were unique. They have like 4 or 5 3D printers in their office now that just churn things out. At the time, it was still, you commissioned a 3D print shop to print your 3D object for you. Oh, thank you so much. You can just drop it there. Anywhere, it's fine. Yeah, thanks. So here's the design and the finite element analysis. So they got the model from the base building engineer. Mustache is looking fine, Bowick. Normally he grows a sweet Sam Elliott mustache. Gotta say, you are a man blessed with facial hair. But I don't know, something about this round, creeping me out a little bit. So they got the base building models from the engineer. They were able to bring it into their software. They had 24 load cases for the 3 different nodes. So that was 372 unique load cases analyzed, which you've seen is pretty common. But this level of analysis, you know, a model like this would take a day to run, maybe 2 days to run. Kind of refining. We don't like to use the word, what did you were talking on the phone call for Assiniboine yesterday, not trial and error. We don't like to use the term trial and error, but that's essentially what it is. You have to conceive of an idea, run it, see if it behaves the way you hope, and then go back and tweak it again and again and again. And then sometimes maybe you get a better idea as you go through the process. So the design on this would be really intense. Kind of going through and managing the software and managing the understanding of the structural analysis of it. Here is a close-up of the weld zone, so you can see the interface between the HSS and where the casting would come in. They then had to coordinate with the foundry. In North America, the foundries aren't big on castings. They see castings as kind of part of the fluid dynamics industry and the rail industry. So rail industry, nobody cares really what it looks like. And the fluid dynamics, the spot that they care about is the inside. The inside where flow or liquids are running through is what they really care about, because they want to not hinder kind of the turbulence of those objects, and they don't care about the outside so much. We're kind of flipping the world inside out for them. So with the foundry, they don't always use the same foundry. They use foundries all over North America. They have used foundries in China, but they have to make sure they're using ones that meet kind of the design standards that they have from here. They did have an incident where they had to return a couple batches of their UPC, but that was more about communication and understanding the same processes. I think they do have a few where they do kind of farm out the casting process. Assiniboine, they were cast in Brazil, right?
Yep.
So really it is about figuring out the uniqueness of that project and what that foundry can offer them. So it is really, it's heavily coordinated with the foundry, because different foundries have different skill sets, and it will show up kind of in the project. They have to understand how the material flows into the casting. They have to understand how it cools, because steel, if it cools too fast, can crack, or how it cools, it will crack. It has to shrink. There is some shrinkage somewhere. They have to have very good control over the alloy mix because they're trying to make it fluid. They're controlling what temperature it melts at, what temperature it solidifies at. Is it weldable? How is it weldable? How does it cure? How does it cool? And they need to meet their tensile yield strengths, their tensile strengths and their yield strengths, and they need to meet their stiffness requirements. So they have to try to meet all of those same things our normal steel makes. And normal steel is cast, but it's very linear. It's very simple. It's not that kind of out there in the world. There's the tooling. We need to make a positive of our object. So the positive can be made out of wood, plastic, styrofoam. They even have wax casting or lost mold casting. So basically, you create in some lightweight material the positive or the actual object you want. It's not the final version because it's in a different material. You then press things around it. In this case, it's often sand. I'll go on with that. That's the next step. So we have a positive of the element. It's usually wood, plastic, or styrofoam. If it's a big casting, the positive will be in a few pieces. They then cover it in a slick, greasy paint so that when you do whatever your negative mold is around it, it will break away. And then sometimes you can reuse that tooling depending on what your object is. So here is a wood positive of the Queen Richmond casting. It seems a little crazy that this negative portion is a positive, but trust me, it is. Here is another part of the positive. So you can see that that is the outside edge of one of those nodes. You can see what they did here is they glued wood together and put it on a CNC machine. So they were a part of creating these files that would be programmed into the CNC machine that would carve out this positive. This is the inside of the positive. Then they have to create the negative mold. So those positives would get put together, and then they would press steel around it. So it's sand with 3 binders that are chemicals that are added into the sand. Normally it's a coarse black sand or even a green sand because of the chemicals. They use fine sand for the facing, so you get a smoother finish. For the Queen Richmond Center, each node used 150,000 pounds of sand. So it's the weight of 750 guys. So each casting used that amount of sand. They reuse the sand. That's a question because we talk about in concrete, or you're going to hear Dave talk next week a little bit about the high cost of sand on our environment. That they reuse the sand in this. So they try to salvage as much of the sand. After it gets used, it burns off all the chemicals, and then they take the sand and then they kind of clean it up, and then they reuse the sand by applying the chemicals again. So here is a painted wood positive ready for the sand to be pressed around it. So you can see that this is the end of one of the elements, and this is going to be, if this portion right here would be the steel part, similar to the steel part, and that would be where they would weld the HSS to. Here's the sand getting pushed into it. The sand, just so that they can move these molds around, they'll actually put rebar in the sand to give it a little bit of structural kind of capacity. You wouldn't want to bang on it too hard because it would start to come apart, but they want to be able to move them around. So you can see that white part was the facing sand, and then here's the dark green sand or black sand with some rebar in it that they can attach some hooks to. They're adding some tubes in there that allows them to help cool the casting or control how it's cooled after they put the molten steel in. So these are almost vent tubes, if you want to think about it, or a place that they can help control how it cools down. Here's them adding more sand into the box. So here is the positive, the wood positive, with the box that allows the wood or the sand negative to be put into it. So they need to worry about venting and heat dissipation when they're casting these things. So the chemicals in the sand need to burn off because it's going to have hot molten metal pressed up against it, and so that's going to be somewhat volatile. If you can see, all of the guys were wearing masks back when it was unusual to wear masks every day, and that was because of the chemicals in the sand. Low risk, but still. And then when they heat it up, you can imagine that those chemicals get burned off and the sand goes back to being sand. So they have to put outlets in it for the off-gassing of the sand. And there is a little bit of off-gassing prior to the pour, which is why they were wearing those masks. So what they'll do is, just to kind of help that process, is once the mold is ready, they will heat it up with a blowtorch and just get some of the preliminary off-gassing out of the way so that the stuff near the surface doesn't damage or show up as a visual on the surface of the casting when they make it. Here is the top of the wood positive painted and awaiting a form to make the sand negative. So that is the top of the casting. And this is interesting. This is a heat sink right here, and I'm going to show you that. So they drop that down on it and then fill it with sand. So here are the vents that they are going to cast into it to make it, to allow venting. Right there, it's hard to see, is the heat sink. Here's the wood positive for the heat sink and for the material feed. So they'll pour molten steel into this, and then they overfill it, and so as it cools off, the last place to cool is where you're going to start to see your cracking. And so they'll make a heat sink be the largest spot on it so that that's where any cracking would occur on the mold. So filling the cope or the top mold with green sand. And here it is filled up. So then they have to assemble the negatives. So that negative was done in pieces by pressing them up against the different wood pieces, and then they have to assemble them. The in-between pieces are lock and key fit. The bottom is the drag mold and the top is the cope mold, so as you pull it off. And the parts that form the hollows are the cores. All of those elements may add to the complexity of a casting. So just a drag and a cope, easiest mold to make. Having extra pieces that are lock and key fit adds to the complexity. Doing hollows or cores really ramps up the complexity. So you can imagine this one that has 4 hollows or 4 cores in the casting is going to be one of the most complex molds you can imagine. So here is the drag or the bottom sand mold, and there is the part that is going to have finished exposed steel up against it. Here are 2 core elements being put together, and you can see all of those are going to have steel cast against it, so they have the white facing sand. Here are 2 of the cores being fit in. I wonder if it's a good place to show you the video of this. Yeah, I'm going to show the video now. Let me just Let me just get this open for you guys. Okay, let me drag this over here so you guys can see it. And let's play the model. So there's the drag mold. They needed to think about how all of these things were going to go together. So there's two of the cores pushed together, being fit in. There's more lock and key fit pieces that are going to come down in pieces and fit around this. So the blue is everywhere that would have facing sand, and the red is everywhere that would have facing sand. And then the cope gets brought in and fit over top, and you can see the part that would be exposed there. So there's an intense amount of engineering just into going into making the mold and fitting the mold and how you put that mold together. So you can see here them fitting in those cores. There is the bottom drag with the cores put in, them starting to put in the lock and key pieces, and then here's the cope being brought over to drop in on top of this. So here's where I was going to show you the mold assembly video. Like I said, I haven't gone through this in a very long time. So casting the steel. It's filled with molten steel, and it takes 60 seconds. Months and months and months of work done in 60 seconds to get it right. Each node was 2 ladles of molten steel per node. The steel is 1,560 degrees Celsius, so insanely hot. In the casting, there's 50,000 pounds of steel used. In the end, the final casting is 30,000 pounds. That 20 pounds of steel that isn't used in the final casting gets taken and melted down and used again. The binders in the sand burned off, and then the sand gets retreated and reused after each node use. So here is, I'm going to show you the video of the filling and the cooling, and then I'm going to show you the images. This one is the material. So here is the steel. Here is the liquid steel coming into the casting. And this is the 60-second video of what their anticipation of the real-time process would be. So you can see that there are 4 spots where it's coming in, and this is showing how those bits are mixing. So you can see 1, 2, 3, 4 basically risers of steel coming in, filling this casting. And here's the heat sink up here. And 4 small heat sinks. So that's it. That wasn't, a sped up version of anything. That is actually how they expect, that is what they anticipated the steel to do, or how it would go as they were filling it. So let me close that. I'm also going to show you now the video of the liquid fraction, or the cooling of the material. So this one is a delayed video of what they would expect. This is over a 24-hour period. This is the steel cooling. And what they want is they want this bit here to cool last, because that's where you're going to have your major flaws happen as it cools. They want this to cool the best. So you could see that it kind of went away from the structural components. And this is going to be the casting that they're left with some overflow bits where extra steel kind of pops out. And so you can start to see really the final shape that's going to happen of this casting. Why can't I close you? Close it this way. Okay. So here is the casting. Here is the bin of molten metal. Oh look, here's where I was going to show that. Did I show it right in? Oh, look at that, I showed it right in the video. So you could watch it directly in the video. What the? Maybe it will only do it if I let it go to the end here. There we go. Just since we've already watched it. And there's the material trace, which I already showed you, and the drag, which I already showed you. So it looked like I did have a place for all of those in the lecture. Where are you? Okay. All right, operating the valves. That guy, I don't know how much he gets paid, but that has to be the most dangerous job ever. He is opening the valves on this thing that is like over 1,000 degrees Celsius, opening that up to pour the molten steel in. It's really hard to actually get an image of the molten steel simply because it's so bright it overpowers any camera. Here you can see the gases in the sand burning off, and you can see it burning out of the riser vents. So when it comes out, it does not look great. It spends 2 weeks in the mold cooling. They remove the metal flasks around the sand. The sand returns to normal sand and it falls on the ground. They cut off the risers. They grind down the bleed lines. So anywhere any of those mold pieces connected together, there's little tiny bits of molten steel. And then they heat treat it to relieve the stresses. So if you guys remember when I talked about in Structures 2 that cold form steel is 350 MPa, and our 350 MPa is 350 MPa except for our W section beams and our channels that are hot rolled into shape, and that hot rolling causes as it cools some locked in stresses. So this heat treatment relieves some of the locked in stresses that happen in, as much as it's a controlled cool down, it's so hot and they can't control the cool down that well that they will sometimes, depending on the forces required, heat treat it to relieve some of the stresses. So here they are removing the cope and the risers. You can see the risers, the vents and the heat sink left there. You can see that the sand, they've just pulled this off and the sand is now all just loose. Here they are taking off the next portion of the metal. You can start to of the metal form. You can see the sand is mostly loose now, and you can see the casting kind of coming out of it. I've been in these foundries, and that sand gets everywhere, man. It's up your nose, it's in your ears. I went home, and it was like all in the cuffs of my jeans. It's just in the air. It's everywhere. It's crazy. So here you can start to see the casting and a bleed line and some of the risers and vents. I love this image of them pulling it out. You can see the risers, and that was where liquid steel actually came in. You can see the heat sink, and you can see the sand falling off. And here it is. Isn't it beautiful? Lovely, lovely piece of work. It kind of looks like crap, but that's because they need to cut all of these down and grind them down and smooth it. So here they are torching off the bleed lines, cutting off the risers. You can see that you can still see some of the bleed lines here. So they've cut off these top ones. You can see that it's starting to rust a little bit too. As it cools down and is exposed to the air, it oxidizes just a tiny little bit. Here it is. Now it's starting to really look like it. Here are the hoist elements cast into the inside that you'll never see. So that was also designed for the lifting loads of this. I love this image. This is them heat treating the node to relieve the stresses. So it basically sat in its own little sauna for a while, heating it up, and then they controlled how they take the heat away to relieve internal stresses. So here's the thing. How do we know it's good enough? Obviously, there's the visual surface review. They compare it to images of castings and say, yep, this meets our AESS, blah, 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 and they judge it based on that. Magnetic particle inspection. They basically put big magnets on it and test how the field tracks through the steel, because they want to make sure there's no internal bubbles and flaws or cracks that we can't see within the element. You know, our normal steel members, we're pros at making them, and we've tested them again and again and again and again. This is a 1, or in this case, 3 off object that we need to make sure is perfect. Isotope radiography, so basically you throw isotopes on it and read what comes out, and ultrasonic inspection as well. So all of these were done on all 3 castings with levels of target levels that were trying to be hit. They then surface treat the outside and machine it to plus or minus 1 millimeter of tolerance at the connections. 1 millimeter is insane tolerance levels. You know, I think the standard in the steel code, I forget what it is right now, but it's really like on a 1-story building, you can have like 6 millimeters of tolerance. And this is meeting less than 1 millimeter of tolerance. So here it is, after machining, basically ready to go. And it looks freaking gorgeous. Look at that, it's ready to go. You can see that it's got tapered edges getting ready to be welded on. So fit up and erection. It needs to be built into the fabricator's process and system on how they'll actually erect these things into place and install them. They actually had to weld on temporary erection tabs, because what they didn't want is to have a welder welding this together while it's being held with a chain and hoist that is susceptible to wind and slight movements. They wanted it to be exact. So what they did is they hoist it into place, install it with temporary bolts that are much quicker to install, come back, weld up most of it, cut off, grind down the tabs, and then complete the welding. Love Walters. One of the things they did was they did a shop fit up. They literally tested that these things would fit together the way they intended in the shop, so that they would have no surprises in the field. So here's their shop fit up. Here is the base for the columns for these things. You can see that it's a big raft slab with buttresses to pick up the angled columns. You can see that the bases are templated, ready to get those elements fit on. They actually cast in a framework to be able to have the kind of cone that is doing the primary structural work. Look at that grid of steel. Beautiful work on that. So then the concrete was cast and these HSSs are installed with temporary shoring. You can see that they had temporary tabs here to temporarily brace these things with work platforms built in. Here they are getting ready to accept the node. Here it is being hoisted in. And here you can see it's in place with these HSSs now being, so there's the platform that temporarily connected them together until they can finalize all that welding. And there's the image of the node. So that is the lecture I wanted to give you guys on castings. There's more cool projects that those guys have done. I wanted to give you one focused on something kind of nearby that the majority of you can go for a walk or a run by and take a look. Some of you may have been in the building. Some of you may have worked in the building. I know one person taking the class has worked with Sweeney, who are also in the project, also work in Queen Richmond Center, 134 Peter. All kinds of cool stuff you can do with castings. So this is lecture 8. Dave is hopefully tonight or tomorrow going to record lecture 9. It's already up on the website, or on Quarkus, so you have access to the slides. And Glass is also uploaded. I'm going to make another one that I'm in the process of making for installations, and I told you I'd add a few slides for facades and veneers, which was actually going to include some of the stuff for glass too. So a lot of it is being covered. We're not, when we were asked to make the kind of course outline for this, we just threw out all the things we could think of, and we were like, oh, the last 3 are kind of going to be light lectures. So we were feeling a little bit sheepish. Since then, Dave has thought of like 5 other lectures he'd love to give you guys. We might just, for your own interest, throw another 1 or 2 kind of presentations we've done in the past up there for you guys. Nothing we're going to test you on, more just because if you guys are taking this course, it's because it's stuff that interests you, I hope. I hope it's not just because you couldn't get into the other lectures. But really cool stuff. So that wraps up castings, and now I get to go make laddu for Diwali with my son, and I'm very excited because it's not something I've made before. I've had it, but never made it, so it's going to be pretty fun.